folks, welcome to another set of Chemistry 1 video notes. Today we're going to talk about the different types of nuclear reactions, how to perform calculations involving half-life, and the similarities and differences between chemical reactions and nuclear reactions. Let's get started. The big idea behind nuclear reactions are that they involve, drum roll please, that's right, the nucleus. This is different than when atoms bond together in chemical reactions, as those involve only the valence electrons, which we'll learn about soon. Nuclear reactions involve all sorts of other particles, including the two you already know exist in the nucleus, the proton and the neutron. Before we get started, let's refresh your memory. The atomic number is equal to the number of protons. We'll call it Z here. The mass number is equal to the number of protons and neutrons. We'll call it A. When we have two atoms with the same number of protons but different numbers of neutrons, we call them isotopes of each other. We can denote an isotope in two ways. We can write the element symbol with the atomic number as a subscript and the mass number as a superscript, both on the left side of the symbol, or we can write out the element's name followed by the mass number of that isotope. For example, we could write carbon-14 like this, or like this. You also probably already know that opposite charges attract each other, and like charges repel each other. For instance, the negatively charged electrons are held around the positively charged nucleus by their electrostatic forces of attraction, the attraction between opposite charges. It would also make sense that our positively charged protons that are really close together in the nucleus would repel each other due to having like charges. If that's the case, why don't they act like two of the same ends of a magnet pushing each other away? Actually, they do. However, there's another force at play called the strong nuclear force, the strongest of the four fundamental forces of the universe. This is the attractive force that acts between protons and neutrons to hold them together. It's about 137 times stronger than the electrostatic repulsion of the positively charged protons, but it only works when the particles are extremely close together. So, the strong nuclear force, which only ever comes into play when protons and neutrons are close together, is more than enough to counteract the repulsive forces between the protons, which allows our nucleus to stay together. We're not going to go too deep into it, but there's a certain amount of energy that's released when the particles of the nucleus bind together. And that nuclear binding energy is what's responsible for the stability of atoms. This is affected by how many protons and neutrons are in the atom. In short, there's a certain amount of protons and neutrons that work well together and create a stable atom. If there's too many or not enough neutrons, the atom will undergo some type of radioactive decay in order to fix that. Before we go much further, let's talk about the different particles that will be involved in our nuclear reactions. Obviously, we have our protons and neutrons, which we know make up the nucleus. Protons can be represented by these symbols. This tells us that we have one proton and the mass number is 1. It's basically the nucleus of a hydrogen atom, but without its electrons. Then we have the symbol for neutron, which tells us that they have the same mass number as protons, but they have an atomic number or charge of 0. Now we're going to get into some particles that may be new to you. Up first is the first letter of the Greek alphabet, the alpha particle. This is the same particle that Ernest Rutherford shot through some gold foil in his famous experiment. An alpha particle consists of 2 protons and 2 neutrons. This is basically the nucleus of a helium atom, so we often use helium's chemical symbol to denote it. The only differences between an alpha particle and a helium atom are that the alpha particle is very high energy and doesn't necessarily have electrons attached to it. A beta particle is simply an electron. More specifically, it's a high energy electron. We denote it with either the Greek letter beta or an E for electron. It has a mass of 0 and a charge of -1. A positron is a positively charged beta particle. Just like an electron, it has a mass of 0, but it has a charge of +1. Last but not least is the gamma ray. Gamma rays are just very high energy photons or light particles. Like any other type of electromagnetic radiation, radio waves, visible light, X-rays, etc., these photons travel in waves. Gamma rays have extremely short wavelengths and therefore have a lot of energy. Gamma rays do not have any mass or charge, so sometimes we write them without any numbers, but sometimes we'll write it with zeros for both the subscript and superscript. Now that we know the particles involved, let's talk about the 5 types of radioactive decay. Anytime an unstable nucleus, which we call the parent nucleus, loses some particles or changes its particles to become a more stable daughter nucleus, we call it radioactive decay. The 5 types of radioactive decay are named for the particles that are involved with them. In alpha decay, a nucleus loses an alpha particle, 2 protons and 2 neutrons. This will cause the atomic number of the daughter nucleus to be 2 less than that of the parent nucleus, and the mass number will be 4 less. Next up, we have beta minus decay, which we usually just call beta decay. For the next 3, it may be helpful to think of neutrons in one of 2 ways. Either as a proton and an electron smushed together, or as a proton with its positive charge missing. If we smush a proton and an electron together, we don't add any to the mass of our particle, and then the charges would cancel out, leaving us with something that looks like a neutron. If we take away the electron from this combination, we're left with just the proton that was there. This is known as beta minus decay, when a neutron turns itself into a proton by spitting out an electron. Since we're adding to the number of protons but keeping the total number of nucleons, or protons and neutrons, the same, our atomic number increases by 1, and our mass number stays the same. This is the only time our atomic number increases. If we do the exact opposite of that, our nucleus captures an electron from its electron cloud, smushing it together with a proton, when we're left with a neutron. Effectively, by adding an electron to the nucleus, we change one of our protons into a neutron. This is known as electron capture. Again, our mass number doesn't change, but this time our atomic number will decrease by 1, since one of our protons turned into a neutron. Another way to accomplish the same thing as electron capture is to simply remove the positive charge from a proton. That positively charged, no-mass particle that gets removed is called a positron. When we release that positron, our proton effectively turns into a neutron, because it now has no charge and has a mass of 1. When we remove that positron, our proton effectively turns into a neutron, because it now has no charge and has a mass of 1. This is known as beta plus, or positron decay. Lastly, sometimes our nucleus has the right amount of protons and neutrons, but it just has too much energy. It can release that energy to become more stable through gamma decay. The gamma rays that get released in this form of radioactive decay are made up of photons, or particles of light, with a lot of energy, but no mass or charge. The only thing that changes about our atom is that now it has less energy, making it more stable. In reality, gamma decay tends to happen in conjunction with one of the other 4 types of decay, but for Chem 1, we're going to pretend it's its own thing. When we're trying to show that radioactive decay is happening, it's not very easy to draw it out. This is why we learned these symbols for the different particles before. We simply write equations such as these to show what's happening. I'm not going to discuss each of these examples, but you should write them down and look closely at the numbers. The big important thing that we're going to practice as far as these equations go is that all of the atomic numbers on one side of the reaction arrow add up to this be the same total as the atomic numbers on the right side of the reaction arrow. The same goes for the mass number. Since gamma particles don't affect the atomic or mass numbers, we have to show the atoms as highly energetic before the change, and less energetic afterwards. Since the parent nucleus is the one with extra energy, we show that by writing a little asterisk as a superscript on the right side of its symbol. The common way to discuss how fast a radioactive isotope will undergo decay is by referring to its half-life. The half-life of an isotope is the time it takes for half of the radioactive atoms in a sample to decay to a less radioactive atom. Half-life data is important because it gives us an idea of how long we can continue to use an isotope before it's no longer effective, like in nuclear medicine, or how long we must safely store a dangerous isotope before it's okay to put back into nature, like with nuclear power plants. To give you an idea of how half-life works, let's take plutonium-243 as an example. Plutonium-243 has a half-life of 5 hours. If I start with 8 grams of radioactive plutonium-243, I'll only have 4 grams of the radioactive atoms left after 5 hours. 5 hours after that, I'll only have 2 grams of them still radioactive. Then another 5 hours after that, only 1 gram of my original sample will still be radioactive. This keeps going and going until I assume you get to the very last particle. We'll do some examples together in class, but for now, that's all you need to know about how this works. There are special equations for half-life that we're going to use in Chem 2, but we're going to keep it pretty simple for Chem 1. There are two other types of nuclear reactions besides radioactive decay: nuclear fission and nuclear fusion. Nuclear fission is when a large, unstable nucleus breaks up into two or more small, medium-sized, stable nuclei. This generally only happens when you bombard or shoot the nucleus with neutrons. Fission releases a tremendous amount of energy. For example, if 1 kilogram of uranium-235 were to undergo nuclear fission, it would release 2.5 million times as much energy as burning 1 kilogram of coal. This is why nuclear power plants are so incredibly efficient in comparison to coal-fueled plants. You might remember the bombing of Hiroshima and Nagasaki in World War II from your history class. Those atomic bombs, and other nuclear bombs like it today, involve mass chain reactions of nuclear fission. This illustration of nuclear fission shows what might happen a little bit better. Say we took an atom of uranium-235 and shot a neutron at it. That extra neutron makes the atom unstable, and it breaks apart into atoms of krypton-92 and barium-141. Releasing massive amounts of energy and a few neutrons along the way. If there's enough of the uranium-235 atoms nearby, those extra neutrons might hit those atoms and cause them to split up as well. When this occurs, we call it a chain reaction. When two very light nuclei combine to make a larger nucleus, we call it nuclear fusion. We usually see this in isotopes of hydrogen, like deuterium or tritium, fusing together to make helium. This releases even more massive amounts of energy than fission does. In fact, this process is what gives the sun all of its power. We've tried to make fusion reactors here on Earth, but so far have been unsuccessful. Since the plasma that's formed has so much energy, we don't have any material on Earth that can contain it. Here's an animation of what happens when a deuterium atom and a tritium atom combine. Notice the two nuclei fuse together, creating a new nucleus with 2 hydrogens and 2 neutrons. This leaves 1 extra neutron to be released out into the wild. We've talked about chemical changes, and now you know about nuclear changes. It's a good idea for us to talk about how they're similar and how they're different. In chemical changes, we change the way our atoms are arranged together into molecules. In nuclear changes, we change the number of protons and neutrons that make up our atoms. In chemical changes, we create different chemicals, but no new elements. In nuclear changes, we do create new elements by changing the number of protons in the nucleus of an atom. In chemical changes, we can speed them up or slow them down with outside factors like concentration of particles, temperature, catalysts, etc. Nuclear changes occur with their own speed, without any influence from outside factors. Chemical changes could absorb or release energy, making them endo- or exothermic. Nuclear changes only ever release energy, making them only ever exothermic. In both reactions, atoms do become more stable. In chemical reactions, that increased stability comes from changing the way the electrons in the atom are shared with other atoms. In nuclear changes, that increased stability comes from changing the protons and neutrons in the nucleus. And finally, in both cases, no particles are ever created or destroyed. Specifically, no subatomic particles like protons, neutrons, or electrons are ever created or destroyed. Well, that's all for today, folks. I hope this video was informative and that you're ready to get some practice with this information. As always, if you have any questions, please ask.